Yeah, good evening. So in the last couple of classes, we were talking about the Portland cement and its evolution over the period of time. And then we have also seen the different types of cement that are available according to the different standards, that is ASTM standards, European standards. And then according to the Indian standards, we have understood the detailed topics related to the different types of cement. And then we have focused on the chemical composition of cement along with the manufacturing process, that is the wet process of manufacturing the cement and the dry process of manufacturing the cement. So in today's class, we are going to focus on one particular topic, which is called as a hydration or hydration of cement. So along with the hydration topic, we'll also be looking towards how to work with the setting of cement and the structure of hydrated cement in the coming classes. So in this class, we'll be completely focusing on understanding the different hydration products, and then we'll be understanding hydration reactions, how actually the hydration will happen, what will be the output of the hydration reactions. All these things we are going to look in this particular session. Fine. So coming to the hydration of cement, so if you want to define the hydration of a cement, it can be defined as a chemical reaction that happens between cement and water. That's the typical definition for hydration. So the chemical reaction that takes place between the cement and water is known as a hydration of cement. So how this reaction will happen? Suppose, let's say you have taken a sample of cement and you have added certain amount of water to the cement. Now, when you add water to the cement, what happens is initially the cement will be in the form of powder. Okay, initially the cement will be in the form of powder, and as soon as it comes in contact with the water, it forms into a paste. Okay, it forms into a paste. Now, to convert the cement from the powder state to the paste state, it should undergo some reactions. Okay, inbuilt, it should undergo some reactions. Those process of chemical reactions is called as hydration of cement. Okay, the process of those reactions is called as hydration of cement. And here it is not just one reaction where you can define the hydration process. So in order to define the hydration process, it's basically a series of chemical reactions. Okay, it's not just one reaction. It should undergo the multiple reactions in order to have the hydration process to the cement. And in the hydration process, what happens is, as I was telling, it's a series of chemical reactions. And here, the chemical reactions are going to happen between the cement and water. Okay, the chemical reactions are going to happen between the cement and water. Now, once the cement and water have the proper chemical reaction, then they are going to find or they are going to form a binding material. At that binding material, we are going to call it as CSH gel. So what is CSH? CSH is nothing but calcium silicate hydrate gel. So we'll be understanding this one once when we go into the chemical reaction process. But for time being, what you need to understand is a hydration is nothing but a chemical reaction that takes place between the cement and water. Okay, in order to convert the cement which is available in the powder state to the paste state, it should undergo some kind of chemical reactions. And those chemical reactions leads to the formation of the binding material. That's a cement paste. So logically speaking, it is called as a CSH gel, that is calcium silicate hydrate gel. And here it's basically an exothermic reaction. Whatever the hydration reactions I was talking about, these are exothermic reactions. Now, what does it mean by exothermic reactions? So logically speaking, we have two types of reactions. One is called as endothermic reaction, and the second one is exothermic reaction. Exothermic reactions are the reactions where the heat will get liberated into the atmosphere. Okay, exothermic reactions are the reactions where the heat will get liberated into the atmosphere. That is why whenever the cement bags comes to the site, if you dip your hand into the cement bag, okay, if you dip your hand into the cement bag, people who are sensitive to cement, what happens to their hands is their hands will start swelling. Okay, their hands will start swelling. Why that is happening? It is because of the exothermic reaction. So logically speaking, whatever the hydration reactions that we are having, all those reactions liberate certain amount of heat. And when they are liberating certain amount of heat, those kind of reactions are called as exothermic reactions. So in the process of exothermic reactions, what happens to the cement grains is they become smaller and smaller as the reaction goes further, deeper levels. Okay, as the reaction goes at a beyond a particular point, what happens to the cement grains is the cement grains becomes very smaller, the smaller and smaller, and hence they are going to produce, these cement grains are going to produce a products which are called as a hydration products. Okay, which are called as hydration products. And here, with this reaction or with this exothermic reaction, whatever the anhydrous cement compounds that are available in the cement matrix, whatever the anhydrous cement compounds are available in the matrix, when these anhydrous cement compounds mixed with each other or mixed with water, they are going to react with each other, and then they are going to form compounds which are called as hydrated compounds. And remember, these hydrated compounds are having very low soluble materials. Okay, when there are anhydrous cement compounds that are available in the cement, when they react with the water, okay, when the anhydrous cement compounds mixed with the water, they are going to react with each other, and with this reaction, they are going to form a compounds which we are going to call it as hydrated compounds. Okay, we'll be talking about what are these hydration products and hydration compounds in some time. And because of these, what this hydration of a cement can be visualized in two different ways. The first one is called as a dissolution, and the second one is called as a precipitation. Now, what is this a dissolution and precipitation? So, dissolution is something in this dissolution process, whatever the cement compounds that are available, all these cement compounds dissolve in the water. Okay, all these cement compounds dissolve in the water, and with this dissolution process, what happens is they are going to produce a supersaturated solution. Okay, they are going to produce a supersaturated solution. And upon this supersaturated solution is getting formed, then the final products, which are called as hydrated products, are going to get precipitated. And that's called as a dissolution. So dissolution is the process of when the cement compounds dissolve in the water, they are going to produce a supersaturated solution from which different hydrated products get precipitated into the atmosphere. And the second process is called as precipitation. In this precipitation process, whatever the water that is available, the water will attack the cement compounds. That means the water will react with the cement compounds. Here, the cement will be in the solid state. Probably you can call it as a powder state. And when the cement is in the solid state, it is going to convert the compounds into the hydrated products. Okay, into the hydrated products. And because of these hydrated products only, the end reactions of the hydration will take place. Okay, the end reaction of the hydration will take place. This is about, in general, the hydration of cement. So if you have to keep it simple, the definition of hydration of cement, it is a chemical reaction that takes place between cement and water. And remember, it's an exothermic reaction. This is the most important one. It is an exothermic reaction. Exothermic means it liberates a certain amount of heat into the atmosphere whenever cement comes in contact with the water. Now, let's understand that in a pictorial view. So here you can see the cement particles are available. Okay, you can see cement particles are available, and here there is no water that is available. It's just that all the white spaces or the voids or the empty spaces between the cement particles. All the gray color materials are the cement materials, are the cement particles, you can say. Now, this is the cement powder. In general, you can call it as cement powder. Now, what I'm telling when I'm referring to hydration, cement comes in contact with the water. Okay, when the cement comes in contact with the water, that process is called as hydration of cement. Now, if you see here, here the cement is going to come in contact with the water. That means it is an hydration process. Okay, during the hydration process, what happens? You can see around the circumference of the cement particles, okay, around the circumference of the cement particles, some products are getting formed. Forget about what are those products for time being. We'll understand that in the later case. So here what you need to observe is when the cement comes in contact with the water, okay, when the cement comes in contact with the water, they are going to produce some products, and those products you can see around the circumference of the cement particles, and those products are called as hydration products. Okay, those particles are called as, those products are called as hydration products. Now what happens? This is just at the initial stage of reaction. Now, as the reaction gets increased, as the duration of the reaction gets increased, what happens is you will find more and more hydration products. Okay, you will find more and more hydration products. Along with the hydration products, they will also leave certain amount of pore spaces in between the cement particles. Okay, it is not that complete hydration products are getting formed. Once the complete hydration products are getting formed, they are also going to have, or we are also going to experience certain amount of pore spaces. All the white color patches are called as pore spaces. So that's how the hydration products or the hydration reaction will happen over a period of time. I hope it is clear now. So now let's understand what are the different phases of the hydration process. So here we have 5 different phases of the hydration process. The first one is called as initial mixing reaction. Second one is called as dormancy. Third phase is called as strength acceleration, speed reduction, and steady development. So these are the 5 phases available in the hydration products or the hydration process. Now let's understand these phases individually. Now, if I have to represent these 5 phases with respect to the temperature that is available in the concrete, so you can see the in the stage 1 how the temperature is starting, and then how it is going to get reduced or how it is going to get changed in each and every phase. So let us understand this graph in a very detailed way with respect to each stage. So first let us understand with respect to the phase 1. So what is phase 1? It is an initial mixing reaction. Now, as I said earlier, initially whenever cement comes in contact with the water, it liberates huge amount of heat. Can you see here in the very first 15 minutes of time, the amount of heat evolution on the y-axis, you can see the rate of heat evolution, and on the x-axis, you are having the time frame. So in the initial phase, that is in the first 15 minutes, when the cement comes in contact with the water, it liberates huge amounts of heat. Okay, it liberates huge amount of heat. That's called as initial mixing reaction. So when cement comes in contact with the water, okay, when cement comes in contact with the water, a peak in temperature will happen. Okay, a peak in temperature will happen. And this is the phase where we are going to get certain kind of wounds or certain kind of problems to our hand when we keep our hand in the concrete, or when we keep our hand in the freshly mixed cement paste or freshly mixed concrete. Why? Because there will be huge amounts of reaction that is going to take place in the first 15 minutes, and in that time when you keep a hand inside the cement paste or when you keep hand in the concrete, your if your hands are sensitive to the concrete or sensitive to the cement paste, you will obviously find certain kind of swelling on the top of your skin. So that's basically because of the chemical reactions that is going to happen inside the cement, and this will be there with the first 15 minutes only, and after 15 minutes it will get reduced. Okay, you can see the heat that is getting reduced, but anyways that we'll talk in the later case. So here what exactly is the compound that is making this hydration or the heat process to get evaluated at a peak stage? It is because of the aluminate compound. So whatever the C3A, so we were talking about the Bogues compounds in the last class, that is C3S, C2S, C3A, and C4A. So here, as I was telling earlier, C3A is something which takes or which requires huge amount of water. Almost 40% of water consumption is taken care by the C3A compound. So here, when C3A reacts with the water, okay, when the C3A is reacts with the water, it leads to the formation of a compound which is called as ettringite. Okay, when C3A reacts with the water, it leads to the formation of a compound which is called as ettringite. And because of this ettringite, the release of the energy from these reactions causes the initial peak. Okay, we were just understanding that okay, when you mix cement and water, it is going to liberate huge amounts of heat, and then when the huge amounts of heat liberation is taking place, at that time, if you keep your hands inside the cement, there is a chance of swelling to your hand. But here, what is the reason for that? Okay, reaction is happening and liberation of heat is also happening. But what exactly is the reason for the liberation of heat at the initial stage? It is the C3A compound which is making this initial peak. Okay, which is making this initial peak in the heat evolution process. That's the first phase, initial mixing reaction. And the second phase is called as dormancy. Okay, and the second phase is called as dormancy. Now, in the second phase, what exactly happens is whatever the reaction that happens in the phase 1, okay, whatever the reaction that happens in the phase 1, Because of that reaction, what happens is the cement particles will get a surface coating. Okay, the cement particles will get a surface coating. That is what I have just shown you in one of the figures here, right? Can you see here? So initially there is a cement material, cement powder, and then when it comes in contact with the water, you can see on the surface of the cement particles, a coating is available. Okay, I'm calling these as an hydration products, but for time being, let us just understand a coating is available on the top of the cement particles. That is the phase. That is the next phase, which is the dormancy phase. So in dormancy phase, what happens is whatever the chemical reaction that happened in the phase 1 because of the C3A compound, all the surface of the cement particles will get coated. Okay, all the surface of the cement particles will get coated. And this coating will keep on increasing over a period of time. Okay, this coating will keep on increasing over a period of time. And in this process, what happens is the heat reduction will get reduced. Okay, the heat evolution will get reduced. Okay, so that is what I was showing in this particular figure. So here what I was telling, so here the cement particles are coated with certain kind of hydration products. Now, as the temperature gets increased, you can observe in the third figure, as the temperature is getting increased, what is happening? These hydration products are spreading throughout the cement matrix. Okay, throughout the cement particles, wherever the cement particles are available, it is going, these hydration products are going deeper inside the cement particles also. That is where the dormancy phase is coming into picture. So in dormancy phase, the coating will get increased, and because of the increase in the coating process, the hydration process will get reduced. Okay, the hydration process will get reduced. You can see in the first phase, a peak is observed, and then a slow reduction or a rapid reduction in the heat evolution process is available. And then in the dormancy phase, that is for the next 2 hours, this reaction will keep on happening. That is, the hydration products will keep on increasing the coating process. Okay, it goes into the deeper levels of the cement particles. And because of this, what happens is the heat evolution process will get reduced. Okay, it is not getting reduced, at least it is almost getting steady in the second phase. Okay, it is almost getting steady in the second phase. So that is how, if you clearly observe here, initially in the phase 1, you can see a peak curve, and then because of the coating of the hydration products getting increased, in the second phase, it is almost coming to a steady level of heat evolution process. So in this phase, there won't be any problem to your hands. Even if you try to keep your hand inside the cement, there won't be much problem as you are going to face in the phase 1. Now here, this is the phase where we are going to transport the concrete. So we have seen the RMC mixers, ready mix concrete mixers, right? So when the concrete is in the dormancy phase, it is possible to transport the concrete from one place to another place, and then you can pour the concrete wherever it is available, wherever it is required. Why it is possible? It is because in this phase, the concrete will be still in the fluid level only. Okay, the concrete will still in the fluid level only. Now, the length of this period depends on individual concrete mix. It may not be same for all the mixes. It depends on each kind of mix. So this is a typical representation for a normal concrete. Okay, maybe M20 or M30 standard concrete, you can say. So the length of this period, it need not be 2 hours for all the types of concrete. Sometimes you are going to use quick setting concrete. Sometimes you are going to use rapid hardening concrete. So in such cases, this period will get changed. This 2 hours of period will get changed. And here, this phase basically ends with the initial setting time of concrete. So we all must have understood initial setting time of cement or final setting time of cement. Anyways, that I will discuss in the next class. But here we are going to focus on initial setting of concrete. So there is a separate apparatus where you can perform the initial setting time for the concrete and final setting time for the concrete. So by the end of 2 hours, you are going to get the initial set to the concrete. Okay, by the end of 2 hours, you're going to get the initial setting time to the concrete. So that leads to the third phase, which is called as a strength acceleration. So so here what is happening, the setting process is happened to the concrete. It is getting started. That means initial set of the concrete is going to get end. That means, so from the next phase onwards, the concrete will attain the strength. Okay, from the next phase, that is from third phase onwards, the concrete will attain the strength. And that's the reason why we are going to call the phase 3 as the strength acceleration process. Okay, why we are going to call the phase 3 as the strength acceleration process. So in this case, what happens is a heat increase happens due to the reaction between C3s and C2s. Okay, heat increase will happen because of the reaction between C3s and C2s. What is C3s? Tricalcium silicate, and C2s is dicalcium silicate. Now, because of this reaction, what happens is a product will get formed which is called as a CSH, that is calcium silicate hydrate. It is not just CSH that is going to get formed. Along with CSH, there are also minor products that are going to get formed. So we'll see that reaction phases very detailed in the next 15 minutes. Okay, but for time being, just understand how this strength acceleration is going to happen. So the strength acceleration is going to happen because of C3s and C2s. So as I said earlier in the Box compound discussion, the C3s is responsible for the initial setting time. Whatever the initial strength that you are going to get, that is all because of the C3s compound. Whatever the latest strength that you are going to get to the cement or to the concrete, it is all because of the C2s compound. So here the creation of the CSH or the formation of the CSH will play a major role in deciding the strength to the concrete. Okay, in deciding the strength to the concrete. If the CSH products are not available or if the CSH products are not forming on a proper way, then the strength of the concrete will get affected. It will get reduced. So basically, in this case, we are going to have the temperatures at around 7 to 8 degrees centigrade. Okay, at around 7 to 8 degrees centigrade. So that's the phase 4 where we are going to come towards the speed reduction. Now, what happened in the phase 3? So in phase 3, the strength will get accelerated. Okay, in phase 3, the strength is getting accelerated. But in phase 4, what is happening? Whatever the chemical reaction that is available, it tends to increase up to a particular point, and then it comes to decrease level. That is within 20 hours. Okay, this phase will happen. So a maximum temperature has now been reached to the concrete. And whatever the availability of free particles that are there, all those free particles are completely mixed with the water. Okay, all those free particles are completely mixed with the water. Now, does the water have any cement compounds to react with? No, there won't be any cement particles where water can react. So because of this, what happens? So since there are no availability of the cement particles, water cannot react with any other cement particles because all the cement particles are completely reacted with water in the first 3 phases itself. So here in phase 4, you might have maybe 1% or 2% of cement particles, but however, that may not be leading to a huge increase in the strength. But here you can still see there is some peak that is available here. Why this peak is available? Because if there are any leftover cement particles are available, they are going to react with the water. But once the all cement particles are going to get react with the water, there won't be any amount of cement particles to react with the water, and hence the heat evolution process will get decreased. Okay, and hence this heat evolution process will get decreased. And this phase is the phase where we are going to get our desired strength. So suppose, let's say you are going to prepare M20 grade of concrete. So when you are preparing M20 grade of concrete, what is your target strength? Your target strength will be the 28 megapascals or 26 megapascals by using that equation F dash CK equals to FCK plus 1.65 S based on the mixed design process. So you are going to get your target strength by the end of phase 4. Okay, you're going to get your target strength by the end of phase 4. Now, what is happening? What is going to happen in the phase 5? So phase 5 is the place where it maintains the steady strength to the concrete. Okay, where it maintains the strength, steady rate of strength in the concrete. The strength will not get increased and the strength will not get decreased. So it will be a steady rate. So that's why we are going to call the phase 5 as the steady development. There won't be any much increase in the strength and there won't be any much decrease in the strength also. So it will be maintained at a static rate. So that's called as a steady development. So the hydration process is now completely slowed down because there won't be any cement particles where they are going to ready to mix with the water because all the cement particles are completely mixed here. Okay, all the cement particles are completely mixed in the first 3 phases. So whatever the leftover cement particles are available, they are also going to get mixed with the water in the first part of the phase 4. In the second part of phase 4, since there are no availability of the cement particles, the heat reduction process will get reduced. Okay, the heat reduction process will get reduced. And because of these, there won't be any change in the strength, or there won't be any change in the heat evolution process. That's why it will be a steady state. Okay, that's why it will be a steady state. And this is how the different phases that are involved in the hydration reaction or in the hydration process. Now we have understood the hydration process. Now let's understand what are the chemical reactions that takes place in all these 5 phases. Let's understand those chemical reactions. So for that, in order to understand the chemical reactions of the products, we need to understand the terminology which is called as heat of hydration. What is heat of hydration? So before that, let us understand what is hydration. So hydration is a chemical reaction that takes place between cement and water, that we know. Now, as I said earlier, this hydration reaction is an exothermic reaction. Okay, what is exothermic reaction? Exothermic reaction is a reaction which liberates certain amount of heat. Okay, exothermic reaction is a reaction which liberates a certain amount of heat. And this liberation of heat is called as heat of hydration. Okay, this liberation of heat is called as heat of hydration. So here the heat will get liberated. Okay, certain amount of gases or certain amount of heat will get liberated. Because of this heat liberation process only, our hands will get swell when you keep your hand or when you expose your hand to the cement paste or the concrete matrix. So that's called as heat of hydration. Hydration is just a reaction between cement and water. And because of the reaction between cement and water, whatever the reaction that is going to happen, it is an exothermic reaction. So what is exothermic reaction? It is a reaction which liberates a certain amount of heat. And this liberation of heat is called as heat of hydration. Okay, this liberation of heat is called as heat of hydration. So here you can see the different Box compounds and their heat of hydration values. Okay, and their heat of hydration value, that is heat liberation values. You can see C3S compound is liberating 502 joules per gram. That means if you take 1 gram of cement, it is going to liberate 500, almost 500 joules per gram. So the most important thing is the C3A compound. You can see the C3A compound is liberating the highest amount of heat, which is close to 870 or 880 joules per gram. So that's how the different Box compounds are going to release the different levels of heat once they come in contact with the water. So as per Box investigation, whatever the total heat that is available, half of the total heat will be evolved between 1 and 3 days. Okay, within the first 3 days, the total heat will get liberated. That is what we have seen in the phase diagram also. So if you have observed, you can see, so half of the total heat will get liberated within the first 1 to 3 days. Okay, within the first 1 to 3 days, you can see almost by the end of 20 hours. Okay, that means almost 1 day of time. So you can see the total amount of heat is getting liberated within 1 to 3 days. It depends on type of cement. Okay, or the type of concrete. But after 3 days, what is happening? After 20 hours, what is happening? There won't be any liberation of heat, or a minimum liberation of heat is there. So that is what the Box had observed. So whatever the total heat that is there, half of the total heat will be evolved between 1 and 3 days. And about 3/4 of the remaining heat will be liberated in the next 7 days. And 90% of the heat will be liberated within first 6 months. After 6 months, there won't be any huge amount of liberation of heat, and then the concrete will be set by that time. So by the end of 7 days or by the end of 14 days itself, concrete will attain the strength, at least 7 days strength or 8 days strength, 14 days strength, it will be attained. So once the concrete is getting the strength, then you cannot find any kind of reactions that is happening on the surface. The reactions will be happening inside the concrete. Okay, we cannot say that reactions are not going to happen. We should think that reactions are going to happen inside the concrete. Only when the reactions are happening, then only the strength will get produced or the strength will get achieved. So the reaction process is continuous throughout the lifespan of the structure. But how much reaction is going to happen in at what period of time? That is the most important scenario. So now, what does these values indicate? So these values indicate that the continuous curing is going to happen in the concrete. So whenever continuous curing is going to happen, that means continuous liberation of heat will also happen. And because of this continuous liberation of heat, the concrete structures will be having the standstill parameters. That means concrete will be stable enough to withstand the loads, whatever coming onto the structures, especially the concrete structures. So heat of hydration basically depends on the chemical composition of the cement, that is CaO, SiO2, Al2O3, Fe2O3, all these compounds are there, right? It depends on the chemical composition of the cement. And if you want to measure the heat of hydration, we have one common process, which is the heat of the solution. You whatever the solution of a hydrated and unhydrated cement mixture is available, that you are going to heat it, and then you're going to mix with the nitric acid and hydrofluoric acid. And whatever the difference between the two values before heating and after heating, that represents the heat of hydration. Again, this is on a plain level, but if you are somebody who is going to study the heat of hydration process in a deeper level, you have to use calorimetry. Okay, there is an apparatus called calorimetry. That apparatus you have to use, and you have to identify the heat reaction process or the liberation of heat process over a period of time. Okay, so now let's understand the chemical reaction during the hydration process. Now, what are the chemical reactions that are going to happen? So here, cement basically consists of the following major compounds. Those are C3S, C2S, C3A, and C4A. We know these are the Bogues compounds. Along with the Bogues compounds, we also have the gypsum, which is represented with CS bar H2. Okay, so these five are the major compounds which are going to involve in the chemical reactions of the hydration process. Now let's understand how these reactions will happen. So first let us understand how the reaction or how the hydration of C3S and C2S will happen. Okay, how the hydration of C2S and C3S will happen. Remember, all the chemical reactions will happen in the presence of water only. Okay, all the chemical reactions will happen in the presence of water. So let's see that. So we have the C3S and C2S compound, and once they are going to come in contact with the water, okay, H2O is water. Once they are going to come in contact with the water, they are going to form a products which are called as hydration products. And those hydration products are CSH and CaOH taken twice. Okay, CSH and CaOH taken twice. You can also call CaOH taken twice as a CH. Now, let us understand this clearly. So when C3S reacts with the water, it is going to form an hydration product, which is called as a CSH. Along with the formation of hydration product, it is also going to get liberate certain amount of heat. Okay, that's a common thing, because once cement comes in contact with the water, it liberates a certain amount of heat. Along with the heat liberation process, it is going to form one product. Okay, when C3S comes in contact with the water, it is going to form a product which is called as a calcium silicate hydrate. And then when C2S comes in contact with the water, then it is going to form a hydration product which is called as CaOH taken place, which is calcium hydroxide. Along with the calcium hydroxide formation, it also liberates certain amount of heat. Remember, heat liberation is constant in any reaction. Now, if you observe a cement particle or the hydration process, this is how the CSH will look like. It looks like an amorphous fiber. You can see it's like a fiber kind of material, like the cotton, you can say. Okay, it appears like a cotton, like amorphous fiber material. So CSH is something, it contains 50 to 60% of the solids that are available in the paste. Okay, whatever the solids that are available, it contains almost 50 to 60%. And it is an amorphous material, and it's a fibrous material. Okay, like a kind of cotton, you can say, and it will have more surface area. The CSH will have the more surface area, and this is something which is responsible for the development of strength. Okay, CSH is something which is responsible for the development of strength. If CSH is not available at a proper rate, then the strength development will not be there for the concrete and also for the cement. Then let us focus on understanding about CH, that is calcium hydroxide. So calcium hydroxide is also called as a Portlandite. Okay, calcium hydroxide is also called as Portlandite. And this is something which occupies 20% of solids in the paste. Okay, it is occupying 20% of solids in the cement paste. Now, it appears like an hexagonal plates. You can see they are going to appear like an hexagonal plates. Whatever the needles that you are seeing, the needle shaped structures that you are going to see, all these are called as ettringite compounds. I'll be talking that in some time. Anyways, don't bother about that. But here just focus on these compounds. Whatever the hexagonal plate-like elements that you are going to see, all those hexagonal plates are called as a portlandite, which is also called as calcium hydroxide. So this calcium hydroxide will be up to 20% will be there in the solids of the cement paste. Okay, 20% of solids available in the cement paste. And here the CH compound is basically embedded in the CSH matrix. So whatever the CSH matrix is available, all these CSH matrix by default will have the CH compound. So I was telling here, so you can see the CSH compound, but when you go into the deeper levels of CSH or around, CH compounds can be separately forming also. But in general, all the CH compounds will be embedded in the CSH matrix. They will be there inside the CSH matrix. So what happens when CH compound will grow? So when the CH compound is growing over a period of time, whatever the pore spaces that are available, it is going to fill all those pore spaces. So if you don't want the concrete to be a void concrete, or if you don't want the concrete to have huge amount of voids, you should have proper growth of CH compounds. If CH compounds are not available, then voids will be there in the concrete. If the CH compounds are growing at a proper rate, then the pore spaces will be completely filled with the CH compounds. But the one thing which is important is CH does not have any contribution towards the strength. Okay, CH will not have any contribution towards the strength. Besides that, it also causes white patches and efflorescence to the concrete structures. Whatever the white patches that you see or efflorescence materials that you see on the surface of the concrete structure, it could be because of the CH compound. One reason could be because of CH compound. So that's about CSH and CH. So CSH will takes place up to 50 to 60% composition. CH will takes place up to 20% of the composition. CSH will be looking like an amorphous material, like a fiber content, and CH will be looking like an hexagonal plates. Okay, crystalline hexagonal plates. And CHH is responsible for the strength compound or the strength development, whereas CH does not play any role in the strength increase factor. Okay, it will not play much role in the contribution towards the strength. Now let's understand this factor, which is called, if you observe C hyphen S hyphen H, and you can also see C hyphen H, you can see the dashes are available. What does these dashes represent and why they are available? So these dashes indicate that there is no strict ratio between the silicon dioxide and calcium oxide. Okay, so CSH, what is C? Calcium. S means silicate. So when you represent a dash between the compounds, it indicates you cannot exactly tell how much amount of calcium is available and how much amount of silica is available. So that's what it indicates. So they indicate no strict ratio between the CaO2 and SiO2 compounds. Okay, it can be changing every time. So when there is no strict ratio, you are going to represent the dashes factor here. Similarly, in this case also, the silica to Si ratio should be in such a way that 0.45 to 0.5. So if that ratio is satisfying, then it is fine, no problem. Okay, the silica to calcium ratio should be in between 0.45 to 0.5. Then the hydration process will happen properly. Okay, then the hydration process will happen properly. That's something which you have to focus on. And then let us understand the hydration of C3A compound. So as I said earlier, C3A compound is a compound which takes or which consumes huge amount of water. Almost 40% of water is consumed by the C3A compound. Okay, and it is also responsible for the flash setting to the cement. I was talking about this in the Box compound. So C3A is responsible for the flash setting of cement. So to avoid flash setting of cement, what you are going to add? We are going to add gypsum to the cement. Let us understand that clearly. So C3A compound is available and then it comes in contact with gypsum. Why gypsum? If the gypsum is not available, then flash setting will happen. So C3A compound will react with the gypsum and it will also react with a compound called ettringite. Okay, it will also react with a compound called ettringite and in the presence of water. Okay, these reactions will happen in the presence of water. So now what happens is you are going to get a compound which is called as ettringite here. So here, first let us understand the path in a different way here. So here, what I mean to say when C3A compound reacts with gypsum, let us understand that clearly first. So here, C3A compound is going to react with the gypsum. Okay, it is going to react with the gypsum in the presence of water. Okay, it is going to react with the gypsum in the presence of water. And then a product will get formed that is called as ettringite. Okay, that is called as ettringite. Then what happens is here the ettringite formation has taken place. Then ettringite will go and react with the C3A in the next phase. Okay, ettringite will go and react with the C3A in the next phase in the presence of water. And when ettringite reacts with the C3A compound, then we are going to get a product which is called as monosulfate. Okay, which is called as monosulfate. Understand this reaction very carefully. So here what is happening? This initially the C3A compound. So let me erase this one and then let me make it. So when C3A compound reacts with the gypsum in the presence of water, then it is going to give a product which is called as ettringite. Okay, it is going to give a product called ettringite. I'll talk about the importance of ettringite and the gypsum content in some time. And then once the ettringite is formed, okay, once the ettringite is formed, then ettringite will come and react with the C3A compound. Okay, ettringite will come and react with the C3A compound. In the presence of water, it produces a product which is called as monosulfate. Okay, it produces a product which is called as monosulfate. So that's how the hydration will happen with respect to C3A compound. Okay, that's how the hydration will happen with respect to C3A compound. Remember here C3A is mixing with the gypsum along with water. It is mixing with the gypsum. But whereas C3S and C2S, if you observe C3S and C2S, they are directly reacting with the water. There are no intermediate compounds for C3S and C2S. When C3S is reacting with the water, it is forming CSH. When C2S is reacting with the water, it is forming CaOH. But whereas with respect to C3A, here we'll have one additional compound which is called as gypsum. Okay, C3A will react with the gypsum in the presence of water, which gives an ettringite compound, and then ettringite goes and reacts with the C3A compound in the presence of water, which gives monosulfate as the hydration product. Now, this is the ettringite compound. Okay, whatever the needle-like structures that you are seeing here, all these needle-like elements, whatever that you are seeing, all these needle-like elements are called as ettringite compounds. Let me show you that. So these are the needle-like compounds. And the monosulfate compounds are these compounds. Okay, monosulfate compounds are these. Whatever the fiber kind of material that you are seeing, all those are called as monosulfate compounds. Remember, these are the microscopic images of the cement. Okay, cement hydration process, that is cement paste, you can say. Okay, fine. So what happens when you decrease the cement, when you decrease the gypsum content, it causes the flash setting to the cement. Why? Because this reaction is very fast. Okay, if the gypsum is not available in the cement, as soon as cement C3A comes in contact with the water, it will not form ettringite. Okay, it will not form ettringite. So when it forms ettringite, only when there is gypsum is available. If the gypsum is not available, the reaction will be very fast and it leads to the flash setting of the cement. Now, if you increase the gypsum content, let's say in general, we are going to use the gypsum content, 2 to 5% of gypsum will be added in the cement. Okay, if you increase the gypsum content, it will delay the setting time and causes expansion in the concrete. If the concrete is getting expanded, again, that's a problem. Okay, in both ways, it's a problem. If gypsum is not available, it's a problem. If gypsum is available beyond a particular point, again, it's a problem. Okay, so ettringite constitutes 10 to 20% of the solid content. Okay, ettringite constitutes 10 to 20% of the solid content, and this ettringite will be stable only when gypsum is available. Okay, only when gypsum is available. So then the hydration of C4AF, it is almost similar to C3A compound only, but as I said earlier, it does not play any role in the strength development. The major role of C4AF is to impart the gray color to the cement. Whatever the gray color that you are seeing in the cement, that is all because of the hydration of C4AF compound. So this is how the chemical reactions will happen in a deeper level. Okay, this is how the chemical reactions will happen in a deeper level, and these are the different hydrated products that are going to get formed with the reaction of C3A, C2S, C3S, and C4AF with the water. Again, C4AF is not the major one that we need to focus on. We need to focus on C3S, C2S, and C3A compound. Okay, so now let us understand these chemical reactions in a much deeper level. Okay, up to here it is fine, no problem with the reactions, but we need to focus more on the reactions here. Now let's understand these reactions on a deeper level. So the chemical reactions that are going to happen during the hydration process are basically because of the presence of water. Okay, all the chemical reactions, whatever that are going to happen, they are all because of the presence of water. Now let's see how those reactions will happen one by one. So first thing is the tricalcium aluminate reacts with the gypsum. Okay, as I was telling, C3A reacts with the gypsum in the presence of water, and then it is going to give a product which is called as ettringite. Here R represents a reaction. So C3A, when reacted with the gypsum along with the water, it is going to give a product which is called as ettringite. Okay, ettringite will be available in the form of a needle-like structure. Okay, ettringite will be available in the form of needle-like structures. I have just shown you. Along with the ettringite formation, it also liberates a certain amount of heat. You can see the value of heat also that is getting liberated because of the C3A compound. 207 calories per gram is the amount of heat that is getting liberated. Here it is not joules per gram, it is calories per gram. CAL means calories per gram. Now, here what is happening to ettringite? Ettringite are basically the large needle-like structures. Can you see the ettringite here? Whatever the sharp needle-like structures that you are seeing, all those are ettringite compounds only. And remember, these ettringite compounds will be stable only when gypsum is available. If gypsum is not available, they will not be no longer available. Okay, they will not be stable. They will be reacting with the other compounds. So here, this ettringite compound does not contribute anything to the strength. Okay, it does not contribute anything to the strength of the cement, but they should be available. At least a part of this ettringite compound should be available. Now, then what happens is the tricalcium silicate, that is C3S compound, will react with the water, and then it is going to give a product which is called as calcium silicate hydrate along with certain amount of lime and some amount of heat. You can see the heat also, which is liberating at 120 calories per gram. Okay, so C3S is reacting with the water, which is leading to CSH, that is calcium silicate hydrate, along with certain amount of heat is getting liberated, that is 120 calories per gram. Now, this CSH, as I was telling, it's a fiber structure, amorphous fiber structure, like the sponge. You can see in a much detailed representation in this figure here. Okay, it looks like a sponge actually. Okay, so the CSH will be like a short networked fiber structure which contributes much greater to the initial strength of the cement and to the concrete. Whatever the strength that you are getting, it is majorly because of the CSH compound. Okay, it is majorly because of the CSH compound. That's how the C3A will react with the gypsum and C3S will react with the water, which leads to the two hydration products. In the first case, we are getting ettringite, and in the second case, we are getting the CSH. And remember, ettringite is more stable only when gypsum is available. If gypsum is not available, the ettringite will not be stable, and ettringite will not play any role in the strength development. So what is the product that is playing the role in the strength development? It is the CSH compound. How the CSH compound is getting formed when C3S is reacting with the water. Okay, fine. So now let's understand the other reaction. Whatever the gypsum that is there, okay, whatever the gypsum that is being used in the first reaction, okay, whatever the gypsum that is being used in the first reaction, once all the gypsum is used, okay, whatever the gypsum that is available in the cement, once if it is completely consumed by the C3A compound, then what happens? The ettringite becomes unstable. Once the ettringite becomes unstable, what happens is it reacts with the remaining tricalcium aluminate. Okay, once the gypsum becomes unstable, whatever the remaining products of C3A is available, then it reacts with the leftover tricalcium aluminate. Then it is going to get formed the monosulfate crystals. Okay, it is going to get formed the monosulfate crystals. That is what I was showing in one of the chemical reactions. So C3A is going to react with the gypsum and then it is going to form ettringite. So once the ettringite is going to get formed, it is again going to get react with the C3A compound. In the presence of water, it gives the monosulfate compound. So that is what I was showing here also. Here I am talking with respect to the chemical reactions. So whatever the gypsum that is available, once the gypsum is completely consumed, then the ettringite compound will become unstable. Then it is going to react with the leftover tricalcium aluminate, which results in the formation of monosulfate. Okay, which results in the formation of monosulfate. Then what happens with the monosulfate crystals is these monosulfate crystals are only stable in sulfate deficient solution. That means the solutions which doesn't have enough amount of sulfate compounds, only in such solutions this monosulfate will be stable. Now, in the presence of sulfates, the crystals, whatever that are there, they will go back to the ettringite compound where the crystals are 2.5 times the size of the monosulfate. They will be much bigger, that is 2.5 times the bigger than the monosulfate crystals. And then it is in this increase in size that causes cracking in the cement matrix. So when the monosulfate crystals or when the ettringite compounds and monosulfate is getting increased or when the size of the monosulfate compound is getting increased, it leads to the cracking in the cement, and that cracking is majorly because of the monosulfate compound. Okay, that cracking is majorly because of the monosulfate compound. Why cracking is happening because of the monosulfate compound? Because it is increasing its size. When the size is getting increased, obviously it will not have enough amount of space to go. So when it doesn't have any amount of space to go inside the material, it will make the crack, and that's how the cracks are getting formed. Now, here the C4AF compound. So here the C4AF is basically the ferrite compound, and the ferrite basically undergoes two kinds of reactions in the presence of gypsum. So the first reaction, what happens is the ettringite reacts with the gypsum and water to form the ettringite compound. Okay, ettringite compounds along with that lime and aluminous hydroxide. You can see here. So the ferrite compound comes in contact with the gypsum in the presence of water, which leads to the ettringite compound. Along with that, you can also see ferric aluminum hydroxide. Okay, ferric aluminum hydroxide. And you can see here, there is no content of heat liberation here because very less amount of heat liberation will be there in this process. So that's why we are not going to focus much on the heat liberation process. And in the next phase, what happens is whatever the ferrite compound that is getting formed in the first phase, this ferrite reacts with the ettringite. Okay, this ferrite will react with the ettringite, and then it is going to form a compound which is called as garnets. Okay, it is going to get formed another compound called garnets. So that's how the chemical composition of the chemical reactions of the cement hydration will take place, and the garnets will take up only a small amount of space and do not in any way contribute to the strength. C4AF, we know it does not contribute anything to the strength. So what contribution will be done by the C4AF? Whatever the gray color that you are getting to the cement, that gray color is because of the ettringite compound. Okay, sorry, not ettringite, C4AF compound. So that's how the chemical reactions will happen. So this is the final chemical reaction that is going to happen. Okay, this is what I have discussed some time back. So in general, if I have to summarize the entire hydration products, so the ettringite will consist of 15 to 20%, calcium silicate hydrate will consist of 50 to 60%, calcium hydroxide, which is basically the lime, it consists of 20 to 25%, and voids will be there up to 5 to 6% in the form of capillary voids and entrapped and entrained voids. I'll talk about what is entrapped and entrained air in some time. But here the major composition is taking place by the CSH product. Okay, this major composition is occupying by the CSH product, and because of this only the strength will get developed to the concrete or to the cement also. So now let's understand what is this entrapped air and entrained air. So here the entrapped air and entrained air, if you observe the entrapped air here, so these are the air bubbles which are large, irregular and non-uniform distribution. Okay, it will be distributed non-uniformly. You can see these white color dots are the air bubbles, and here the air content will be approximately 1.5%. Okay, but whereas in the entrained air, what happens is These are microscopic and spherical in shape, which are having the uniform distribution. In the entrapped air, the voids will be having no definite shape. But whereas in the entrained air, it will be the voids will be having the definite shape. The air voids will have the definite shape. And this entrained air will be up to 4 to 6%. But whereas entrapped air will be up to 1.5%. And due to the mixing process and insufficient compaction, these entrapped air will form. Okay, when you don't do proper compaction to the concrete, the air bubbles will get formed or the air voids will get formed. And when you have the air voids in the concrete, it leads to the decrease in the strength. But whereas entrained air, this air is something which is intentionally created inside the concrete because of some properties that we'll discuss once when we are talking about the admixtures topic. We have the air entraining admixtures. There we'll talk about that. But for time being, just understand that the entrained air or the air which are intentionally sent into the concrete by using certain kind of admixtures known as air entraining agents. Okay, known as air entraining agents. Suppose if you want to determine the hydration reaction, you can determine by measuring the calcium hydroxide in the paste and then the amount of heat evolved during the hydration process can be measured by using calorimeter. I was telling about this one. Okay, you can use any type of calorimeter. Again, it depends which values you are focusing on. But if you want to get the hydration process or the hydration reaction of the cement, you can use either isothermal calorimeter or adiabatic calorimeter. Okay, and then couple of others also, but these are all not the better ones. So the better one could be the either by using the isothermal calorimeter or adiabatic calorimeter. And this is the entire summary of the chemical reactions that we have seen so far. And the Box compounds are these. Okay, C3S, C2S, C3, and C4AF. You can see the reaction time of each Box compounds, the strength development and its setting time, okay, along with the heat evolution process. You can see here C3A is something which is liberating huge amount of heat, very high amounts of heat evolution. So that's the entire summary of the hydration reactions and the behavior of the Box compounds in the process of hydration process. Okay, in the process of hydration process. Now let me keep that entire thing, whatever we have discussed from the very first class, all the chemical composition of the cement to the hydration products. Let me keep that entire thing in a simple schematic representation. So here we have the component elements, that is lime, silica, alumina, iron oxide, all these things. These are the basic raw materials that are required to prepare the cement. And then when these compounds reacts with the oxygen, then we are going to get oxide compounds, that is CaO, SiO2, Al2O3, and Fe2O3. Okay, this we have seen. And then when these component oxides will form the component compounds, that is Box compounds, C3S, C2S, C3, and C4F. Once Box compounds are getting reacted with each other along with the presence of water, we are going to get different types of cement. Okay, we are going to get different types of cement. And based on these, the hydration products will get formed. Maybe in the form of gel, that is CSH gel, calcium silicate hydrate gel, and the second one is calcium hydroxide, which is CaOH taken twice. This is the entire summary of the first class to this class, that is starting from the chemical composition of the cement to the formation of the hydration products during the process of hydration of the hydration of the cement. So that's how the entire process goes on. Now, next we are going to focus on the different tests on physical properties of the cement. So what are the physical properties of the cement? Let's understand this and then we'll discuss the remaining topics in the next class. So what are the different physical properties of the cement? So physical means as you see with the naked eye. Okay, as you see with the naked eye, what should be the properties of the cement? That's what physical properties. You have to touch that and then you have to feel it and then you have to determine the property. Such kind of properties are called as physical properties of the cement. So the first property is called as a fineness of the cement. Okay, the first property is called as fineness of the cement. So usually fineness is something which measures the size of the cement particles. Okay, if you want to measure the size of the cement particles, you have to measure the fineness of the cement particle. Suppose, let's say in your houses, if you are preparing or if your mom is preparing the chapati or roti, first what they will do is they'll take the wheat flour or the rice flour or whatever the flour they are going to take, and they are going to sieve it, right? So once they are going to sieve, what they are going to get, whatever the fine particles that are available, that will pass through the sieve. Okay. Similarly, fineness is something which is the measure of the size of the cement particles. So the typical grain size of the cement particles will be 0.0072 to 0.2 mm. This we have seen in the very first class also. And the second physical property is the setting time of cement. And here setting time of the cement is something which is determined by using the initial setting time and final setting time. Anyways, we have the test methods for these. We'll talk about that in the next class. So that's what the second property, that is setting time of cement. And the third property is called as soundness. It is because of the presence of excess slime. Okay. Soundness refers to the ability of the cement to not shrink upon hardening. So if the volume change is happening, that is called shrinking. Okay, if the volume change is not happening, it is because of the sufficient quantity of lime. If you have excess amount of lime, then the cement will become unsoundness. That means the cement will get shrink, or the volume change will happen. Okay, the volume change will happen. That's the third property. And then the next property is the compression test, where we are going to cast the specimens using the mortar, and then we are going to measure the strength of the strength of the cement paste, not the concrete, cement mortar. So you should be getting, at the end of 3 days, you should get the strength of the cement not less than 16 megapascals, and at the end of 7 days, you should get not less than 22 megapascals. That's the fourth physical property of the cement. And the next one is heat of hydration. This is what we have discussed so far. And usually 120 calories per gram of heat will get liberated. And the last property is the specific gravity of cement, which will be approximately 3.15 for ordinary Portland cement. It changes. The specific gravity of cement gets changed based on the type of cement that we are giving. Are we using OPC 43, 53, or PPC, PSC type of cement? So it changes with the type of the cement. So these are the different physical properties of the cement, and then the consistency. Again, this we are going to discuss in the next class itself. So these are the different properties of the physical properties, not the properties, the physical properties of the cement. So that's all from my end for this. Any doubts, you can post it in the comment box. And there is a WhatsApp group link which is posted, which is available in the description of this video. You can join in that WhatsApp group for the discussions related to the civil engineering, especially the different aspects of civil engineering, maybe the concrete technology or the structural analysis, whatever that we want. So we'll be discussing all those things in that community WhatsApp group. So thank you for joining.